Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, a section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles, where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps, or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures.
When we talk about the global electric circuit, we are describing how electricity naturally flows throughout Earth's atmosphere. It can be generated by the interaction of solar wind with Earth's magnetic field, down to the electricity that individual clouds produce. Clouds that produce lightning in a thunderstorm, for instance, feed electricity into the global circuit also. They're all a part of the same system. While we have known for a while that electricity exists in the atmosphere, scientists are just beginning to understand the relationships between the different events that affect it. Could the amount of electricity in the atmosphere change the way clouds and storms develop?
Electric field in Earth's atmosphere. For decades, scientists have speculated about a hidden force in Earth's atmosphere, a global electric field that could hold the key to life on our planet. But until now, it was a mystery, waiting to be uncovered. On a frigid morning in May 2022, a team of scientists set out on a daring mission. They launched a sounding rocket called Endurance from the remote archipelago of Svalbard, just a few hundred kilometers from the North Pole. Their goal? To measure a faint but powerful electric field in Earth's atmosphere. This hidden force is known as the ambipolar electric field. First predicted in the 1960s, this field results from a delicate balance between positively charged ions and electrons in the upper atmosphere. But why is this electric field so important? It turns out this subtle force shapes the very structure of our upper atmosphere. It helps control how quickly a planet's atmosphere escapes into space. This could be a crucial factor in making Earth habitable, while neighboring planets like Mars and Venus lost their thick atmospheres over time. Earth's magnetic field plays a crucial role too, guiding charged particles along its lines, like a cosmic highway. Unlike Venus or Mars, where atmospheric escape can happen from any direction, Earth's magnetic field channels this escape to the poles. This may be one reason why our atmosphere has endured, while those of Venus and Mars have thinned over time. Now, the team has NASA's approval for a follow-up mission with a rocket named Resolute. This mission aims to gather even more data, pushing the boundaries of what we know about Earth's atmosphere and its hidden forces. Understanding the ambipolar electric field isn't just about uncovering Earth's secrets. It's about understanding what makes a planet hospitable, why Earth has remained a cradle for life while Mars and Venus turned barren. It's a reminder that even the faintest forces can shape the destiny of a planet.